Imagine for a second that you weren't just a learner today, but a master detective. Only instead of dusting for fingerprints or interviewing suspects at a crime scene, you're searching for hidden clues in a massive, totally chaotic sea of data. That is exactly what we're doing as we explore the fascinating world of unsupervised learning. Think of it as the ultimate data detective's toolkit, a powerful way to make sense of the unknown and uncover incredible insights that are literally hiding right under our noses. To really understand why this toolkit is so powerful, we have to start by asking a pretty tense question. What actually happens when our data has no labels? You see, in standard supervised learning, we feed the computer nicely labeled data. We tell it exactly what it's looking at so it can learn to identify it later. But let's be honest, real life is rarely that neat and tidy. Real life is incredibly messy. Most of the data generated in the world today doesn't come with helpful little tags telling us what it means. It is just a raw, massive pile of unknown information. So the crucial point is that unsupervised learning is a machine learning approach where algorithms learn entirely from that unlabeled data. The model is never, not once, given the correct answers or any predefined categories. Instead, it acts just like our master detective, sifting through all the evidence to discover hidden patterns, underlying structures, and complex relationships entirely on its own. Here is our roadmap for the explainer so we can keep this journey totally manageable. First, we'll look at the unlabeled data problem. Then, the 3 main learning tasks. Next, we'll open the toolkit for the clustering algorithms, followed by reducing dimensions and finding rules. Finally, we'll wrap up with the real-world impact and future. Starting right off with Section 1, the unlabeled data problem, making sense of the unknown. Let's anchor this in reality for a second. Picture a massive online e-commerce store. They've got millions of customer records, every click, every purchase, every single time someone lingered on a product page. But they have 0 predefined categories. No human has gone through and manually tagged a customer as a bargain hunter or a luxury buyer. It'd take forever. The goal of unsupervised learning here is to automatically group those similar purchasing behaviors. Without any human intervention, the algorithm just finds the natural segments within the customer base, which lets the business actually understand who is shopping on their site and vastly improve their marketing strategies. Okay, let's dive into this and look at Section 2, 3 main learning tasks, categorizing the detective's toolkit. So how exactly do we solve this unlabeled data problem? Well, our toolkit is mostly broken down into 3 main task categories. First up is clustering, which is organically grouping similar data points together. Second is association, which is all about finding hidden relationships between disparate items. And third is dimensionality reduction, which means reducing massive feature sets while still preserving all the important information. Let's shift our focus to that first specific category. Section 3, the clustering algorithms, grouping the unknown. One of the most wildly popular tools in this entire field is called k-means clustering, and it follows 5 exact steps. Step 1, you choose the number of clusters you want, that's the k. Step 2, the algorithm randomly places cluster centers in the data. Step 3, it assigns each data point to the nearest center. Step 4, it recalculates the center of those new clusters. And finally, Step 5, it just repeats this process until the clusters stabilize and stop moving. Going back to our e-commerce example, k-means could take customer age, income, and purchase history and completely automatically segment millions of people into budget shoppers, premium customers, or frequent buyers. It's incredibly fast, though you do have to play a bit of a guessing game with that k number upfront. If you don't want to guess the number of clusters upfront, that leads us perfectly to hierarchical clustering. This method builds step by step and is usually visualized as a tree-like structure called a dendrogram. There are 2 ways it does this. Agglomerative clustering is bottom-up. It starts with every individual data point as its own cluster and gradually merges them into larger ones. Divisive clustering is the exact opposite, a top-down approach that starts with everything in one massive cluster and gradually splits them apart. But what happens when your data is noisy or shaped weirdly? Well, enter DBSCAN. While k-means forces you to guess the number of clusters and totally struggles with outliers, DBSCAN automatically identifies dense regions, determines natural cluster shapes, and spots isolated outliers all by itself. Imagine you're analyzing raw GPS data to find crowded areas in a city. DBSCAN will effortlessly identify the densely populated city centers and then flag the isolated, random GPS pings out in the middle of nowhere as anomalies. It's an absolute game changer. But what if your dataset has thousands of features? That brings us to Section 4, reducing dimensions and finding rules, simplifying clues and spotting patterns. We've talked a lot about grouping data, But if you have thousands of features, the sheer volume of clues is completely overwhelming. I want you to think about the number 10. Large datasets often contain tons of redundant information. If you have a dataset with 100 different features of customer behavior, processing all of that is painfully slow. Enter Principal Component Analysis, or PCA. PCA can actually take those 100 complex features and reduce them down to just 10 highly informative features. By reducing dimensions, we drastically speed up training time and simplify everything, all while keeping the core information intact.
Now, what's really interesting about this slide is the contrast between PCA and another tool called t-SNE. Both of them reduce dimensions, but with entirely different priorities. PCA acts globally. It just wants to simplify the data to speed up processing. t-SNE, on the other hand, is hyper-focused on preserving local relationships. It is the absolute go-to tool if you want visually explore high-dimensional data in 2D or 3D space. You literally get to see the hidden patterns with your own eyes. The final tool in our kit is Association Rule Learning, specifically the Apriori Algorithm. Look at this, bread to butter. This algorithm is designed to discover items that frequently co-occur. A supermarket analyzing millions of receipts might suddenly discover that customers who buy bread almost inevitably walk out with butter. By finding these hidden if this, then that relationships, businesses can entirely restructure their cross-selling strategies to boost sales. Let's transition into our final segment here. Section 5, Real-World Impact and Future. Case closed. And this brilliantly illustrates everything we've just talked about. This is your ultimate master summary cheat sheet. We have our clustering tools, k-means, hierarchical, and DBSCAN. We have our dimensionality reduction tools, PCA for efficiency, and t-SNE for visual exploration. And finally, a priori for association rule learning to find those hidden relationships. You might be wondering, where are these algorithms actually being used? The answer is everywhere. In e-commerce, they're powering the product recommendations you see daily. In banking, they run quietly to instantly detect fraud. In healthcare, they are grouping patient data to discover disease patterns humans literally couldn't see. And in cybersecurity, they establish what normal network traffic looks like so they can instantly identify threats. The real-world impact is massive. Of course, we have to weigh the pros and cons fairly here. The advantages are incredible. It requires absolutely no labeled data. It uncovers patterns humans would miss, and it vastly reduces manual effort. But there are real challenges. Because there are no labels, the results can be pretty hard to interpret. There's no answer key to tell you if the model got it right. And as we saw with tools like k-means, these algorithms depend heavily on data quality and require very careful tuning. Even with those challenges, the future outlook is incredibly bright. Right now, researchers are actively combining unsupervised learning with deep learning. As data volumes continue to absolutely explode, this fusion is going to lead us toward vastly smarter recommendation systems and much more intelligent AI models that can understand the world without needing humans to painstakingly label every single thing. Which leaves us with one final provocative thought to ponder. As you look at the data in your own life, your own business, or your own studies, what hidden patterns are just waiting to be discovered? The clues are out there, sitting in the unlabeled chaos, waiting for you and your new data detective toolkit to bring them to light. Thank you for joining me for this explainer, and keep exploring.